a lot of kind of background information on how circuits work. A lot of what we're covering today is not going to be mathematically relevant to um, the rest of the class, but we still need to talk about it because it's best to understand why circuits work to go through and then do the math behind them. So last time we talked about units. Everything in this class is SI and SI based units. So that means using a lot of prefixes or engineering / scientific notation. We talked about significant figures. Most of the things in this class are going to be 2 to 3 sig figs. For doing that, and we are not going to use the round to even rule. We're just going to do greater than or equal to 5 rounds up. 4 greater or less than or equal to 4 will round down. Any questions from last time? I know this looks like we're covering a lot. Chapter 2 has a lot of kind of short sections. Some of this, especially the first 2 sections, we're going to go through a little bit on the quicker side. Hopefully, not all of that is new information. So the main things that we're going to need to go through, though, and kind of start introducing is this section here. So these are the probably new concepts for that we'll be bringing forward with the rest of the semester. All right. If I asked you to draw an atom, right, you would hopefully draw it with some sort of nucleus and probably some sort of electron cloud in some way, shape, or form. Very common pictures for what that could look like, where you have your nucleus and you have something orbiting around it. Right? Something like this, typical representation for hydrogen. We could go through and make it more complicated. You can make it 3D, but they all typically look the same with how you start having those represented in textbook images, as well as just kind of like pop culture usage of the atom as well. So for the atom, you have your protons. These are your positively charged objects. They are inside of the nucleus. You also inside the nucleus have the neutron, neutral charged object. And then in the electron cloud, you have the things called electrons, and those are going to be your negatively charged particles. So with all of these, you might see a representation that is some sort of variant of this. So this is sometimes referred to as the Bohr model. And what this does is you have your nucleus with your protons and neutrons. And then around it, you have the electrons. With the Bohr model, I don't personally think this particular image does a great job explaining what the Bohr model actually goes through and looks at. But if we kind of look at it, we can see that there's some electrons a little bit closer to the nucleus, and we have some electrons a little bit further away. Those distances are telling us that there's a specific energy level that an electron can have. This is something that is atom-based. You can hand solve hydrogen with the Bohr model, nothing else. The beautiful model that poorly works out. We then go to the periodic table. So this is I believe it's the most up-to-date version of the periodic table. Some of the, if you look at older periodic tables, some of these later elements will be like UUM, because they don't have names, but they all do now. So with this periodic table, it is organized by the number of protons that are inside of the nucleus. Now, if we're being honest, for circuit purposes, we are not going to care a lot about the individual elements. We are going to be talking a lot about very specific elements right along this line here. Yes, I guess this part here. So copper, silver, gold. I think there's an example I have somewhere in the class with platinum in it. But those are typically your conductors that you would go through and see for your circuit. So a lot of what we'll talk about when we're talking about wiring, it will be in that part. But we're going to make some nice approximations that it's not going to really matter what we have. So for this here, we now know a lot more about the atom in comparison to when circuits were being done. So if you've taken chemistry before, maybe you've talked about it a little bit. Is it easier to get a proton out of the nucleus and out of the atom, or an electron out of the atom? It's going to be a lot easier to get that electron out. So we are very gently going to touch some stuff about the quantum model for atoms because it explains how we're going to get those electrons out of the atoms themselves. And with those electrons, once they start moving in a direction, like all of the electrons start moving in the same direction, that's going to be what goes through and gives us our current. So with the stuff that I'm going to talk about, so hopefully you understand where the charges come from. But over the next couple slides, everything we're talking about, just understanding how do you get these electrons to then go through and create a current. Not expecting you to memorize it. I'm not expecting you to draw me pictures, but it's nice to understand where this stuff comes from. So if we go through and we look at the quantum model, what happens is we get these energy levels where the electrons can exist in. And the closer you are to the nucleus, the lower the energy is going to be. That comes from Coulomb's law, not important for this class. As you get further and further away, that energy or that attraction between the negative and the positive charges gets smaller and smaller. And eventually, if an electron has enough energy, it can be ionized. So with the ionization, that basically just means that electron is now free and it is no longer associated with that particular atom. So with these energy values, it is dependent on what element you happen to have. This one here happens to be hydrogen. This is the one that we can hand calculate. As soon as you get to helium, it is no longer hand calculatable. So that's why the picture is almost always shown for hydrogen, even though you're not going to have hydrogen responsible for creating an electric circuit here on Earth. It's just highly inefficient to go through and do so. With these energy levels, they kind of get grouped around a little bit. So when they have a bunch really close to each other, those are typically referred to as shells. Those are going to be your rows on the periodic table. But we should note that with these two down here, technically they are not separate shells. If we looked at a real periodic table with how it would be represented, this lanthanoid row and this actinoid rows, those go right here. They belong in 6 and 7. So again, background information, a lot of these not very stable or, very common. You're not going to have circuits made out of these components. When you have these small shell things, so when you're looking at, let's say we have platinum, that's going to have 70 electrons when it's neutral. What's going to happen is there's going to be some electrons that are really close to the nucleus. They're going to be more tightly bound. So it's these far away electrons that we're going to be pulling to go through and start creating our current. And in particular, if we think about the elements that are good electrical conductors, they typically fall in row 3 to row 12, or sorry, column 3 to column 12. That's typically going to be where they are. And there's something nice about these particular rows, and that has to do with what is referred to as their valence electrons or their empty electron shells. Before we get into those, any questions so far? So, highest energy level, typically the furthest away. Those are the valence electrons for d orbitals, and we'll see why that's going to be the case a little bit on the next slide. Electrons, once we get into those d orbitals, they're pretty far out there due to the weird shapes that they happen to be. And with these weird shapes, what ends up happening is because they're far away, they're closer to that ionization energy, it's really easy to just start stripping those electrons. So in the case of metals, which is what we're typically going to care about in this class, you strip those electrons and they become what is referred to as the sea of electrons, and they just kind of hang out until we force them to move in a specific direction. So this is another representation of the atom. So here we have 29, which is our copper, one of our more common conductors that we'll be talking about a little bit here. With that electron that is labeled as a valence electron, it's far away. It's by itself. There's a lot of, again, background math stuff that explains why that's the case. Not important for this class. But basically, it's really easy to get that one valence electron ripped away from copper. And what that will do is, now it's just going to hang out. But if I apply, as we'll see a little bit later, a voltage, it's going to cause it and all the other valence electrons that are now stripped away from their original atom start moving in a specific direction. So the reason for this being the d orbitals, which again, column 3 to column 12, those are where your d orbitals are your non-filled orbitals. Far away, easy to strip away those valence electrons. Has anybody here ever seen the quantum model for electron shells? Right, you're in for some crazy shapes. So before I show you the shapes, again, you are not expected to know what these are. You're not expected to draw them. I just think that beneficial to understand why these d electrons are so easy to rip off. So this is the quantum model. With the quantum model here, this is our s orbital. So these are the first electrons that you're going to have. Depending on how far you might have gotten into chemistry, you might have seen these p orbitals represented a little bit more like dumbbells, but they're just kind of two jelly beans kind of on top of each other. And then you get into the d orbitals. And now you've doubled what they look. There's 5 different types of d orbitals. And so you have kind of these ones where you have 4 kind of interacting with each other. And then you have the one that everybody affectionately refers to as the donut. So if I was to go through, I am going to very poorly draw what this looks like. If I go through to try to draw one of these earlier ones in column 3, I'm going to have a 1s. I'm going to have 2 electrons in there. That's going to be. I'm then going to make the 2s, and that's going to be a sphere that's on top of it. That's going to get me my 3rd and 4th electrons. And then I'm going to go through and I need to add the p's. So, right, that's ish gonna look something like this. We got a set up here, and we got a set kind of coming in and out of the plane. Again, poorly drawing for doing this. So that gets us all the way over to 10. I then need to go through and do the same thing from 11 to 18. So I have another s orbital, and then I have another set of p orbitals, which look right. Oop, they're bigger, so they go something kind of like this, and they make a shape that I can't draw. The others look something like this. And then we have another s orbital, and then we get into the d's. With the d orbital, let's draw this donut one that's, I think, the most fun one to attempt to draw in 2D. What it happens to do is it's way out there. And even its donut-y behaviors far extend beyond the atom. So a lot of different effects going on at the same time, but basically you can just strip that electron off that's hanging out here by itself pretty easy. And those are the electrons that are important for this class. And they help us go through and classify all of our materials into 3 different types. So before we do those, any questions so far? All right, the 3 types of materials: conductors, semiconductors, insulators. All materials get broken down into one of the 3. What's a conductor? What might you have heard about these conductor objects? Yeah. The official textbook definition is readily allows current. What it is. What are some examples of conductors that you might have seen or heard of? Copper, fantastic conductor. Not the best, but it's pretty good. What else? Gold, not the best, but for some reason people think it is. What else? Platinum's pretty good. Platinum, not the best. However, it's one of the best for controlling what's going on. So it's typically not used for wiring unless it's needs to not react with stuff. It's used a lot more for electrically charged chemical reactions on a surface. So catalyst type things. Anything else? Silver is the best. So all of those are examples of metals. Are there any non-metal examples you guys know of that is a conductor? What type of water? Yeah, so salt-based waters, ionized waters. Pure water is an insulator. But salt water is a conductor. So semiconductors are kind of a weird thing. They are in between a conductor and an insulator. They can have a current, but it takes a little bit of effort. So with semiconductors, you can get there, just have to do a little bit more. What might be an example of a semiconductor? It's okay if you don't know any. Silicon is the singular most common type of semiconductor. I'm not expecting anybody else to know the second most common one, which is germanium. So basically, a lot of the stuff that you have going into your computers, those tend to fall a little bit more into semiconductors for going through and doing that. You can have element semiconductors, but more often than not, they are compounds in some way, shape, or form that go through and create a semiconductor. What's an insulator? Well, in general though, before we look at some examples, which water indeed is one of them, what does an insulator probably do? It's a poor conductor. It is pretty good at blocking current from going through. Examples, water, yes, is one. What else could be an example of an insulator? Plastics, rubbers, ceramics is another one. What else? Clay is a good one. Anything else? Basically a lot of non-metals kind of go into that. There is a weird little caveat with an insulator. So the idea of a conductor is it's pretty easy to have that electric current and have it flow. A semiconductor, somewhere in between a conductor and an insulator, takes a little bit more effort to have a current, but it can be there. Insulators can become a conductor if you have a strong enough source. Now, please understand, I am not telling you to do this, but you can yourself, like you can go look at the videos that I'm okay with, but don't try it. But you can look up videos online of people buying those really unnecessarily expensive wood tables where they'll connect multiple car batteries to it. And what they do is it then has a pattern as if it's been struck by lightning kind of going through it. Wood typically is considered an insulator, but if you attach enough car batteries to it, it now breaks down and becomes a conductor along certain paths. Air is a fantastic insulator. What does lightning travel through? Travels through air, right? So there's a big enough source that then causes air itself to become an insulator, or conductor. So with semiconductors and insulators, at some point, every material becomes a conductor. We're just talking about kind of normal levels of, if I attach a 9-volt battery, is anything going to happen? If no, probably a semiconductor and insulator. If yes, it's probably a conductor.
So is that just because it's getting enough energy level, it's kicking it up to the D orbital?
It doesn't necessarily have to go into the D orbital. It can just immediately just strip it from wherever it's at. Because I think wood's mostly carbon, so it doesn't have a D orbital, so it's just ripping it from it. Yeah. Any other questions? All right, so charges are our positive and our negative charges, so our electrons and our protons. They are one of the, I don't want to say few, one of the examples for having a long range force. So what that means is they don't physically have to be in contact with each other to interact with each other. So what do you guys know about, let's say, two positive charges? Are they going to attract or repel? Why do you guys say repel? You're right, but what might you have heard to give you that information? Opposites attract is very much where some of this comes from. If opposites attract, that means the like ones have to repel. So in general, the further away, the lesser the force. So if there's uncharged particles, so if you tried to bring an uncharged, let's say you have two plastic pens, they are not electrically charged with each other, so there's no electrical force between them. Opposites do indeed attract. So those would be attracted to each other. It's part of the reason why electrons orbit around positive charges. And then the like ones are going to repel. So this is important stuff, kind of if you need to go through and start looking into the theory of how you kind of have limits for how big your current can be. So this is, if you want to talk about that, I'm happy to do so. It is very unnecessary for this class, but there's a lot of cool theory stuff that goes into all of this and how it then affects your current values. So it's there. We're not going to worry about it too much, other than it is stuff that at the end of the day technically affects our current values. However, it's such a small contribution, we are going to be ignoring it moving forward. Okay, a little bit more just talking about charge stuff, then we'll get into stuff that's actually useful. But any questions so far? Right, so the unit of charge is the coulomb. This is named after, forget his first name, Coulomb, of Coulomb's law, which he went through and investigated a lot of the interactions between charges together. The most logical symbol, of course, for charge is the letter Q. So that's going to be the symbol that you would utilize for that. And the unit, so the unit of charge is the coulomb, it is capital C. When we go through to talk about our current, that is in amperes, it's related to the coulomb. When we talk about volts in a little bit here, it is technically related to the coulomb as well. Tesla's not. Farad is. So some of the stuff we're looking at in this class, even though we're not going to explicitly see the coulomb involved, it is something that is in part of that unit in the background. The charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. And so when you go through to look at the interactions between a single electron and another electron, or even a nucleus that has 29 protons in it, it's a really, really, really small force. This is going to be why we go through and ignore it a majority of the time. That small interaction between moving electrons with their and the atom, tiny force, doesn't really affect our calculations. This is a weird fact that the textbook is going to like to bring up when it's talking about sizes. So it would take 6.25 times 10 to the 18 electrons to make 1 coulomb of charge. This is going to be something that kind of comes back and talks about why the farad is so small in the future, because it takes a lot of electrons to make big charges. I'm going to show you an equation. We are never going to see it again. So it's up to you on if you want to write it down or not. If you needed to calculate the charge of an object, you can take the number of electrons and divide it by the number of electrons per coulomb. Or take the charge of a coulomb or of an electron and multiply it by how many you have. We're not doing it in the class. It's not useful for us, but it's later when we talk about capacitors, we'll talk about charge on them. This is the calculation that's technically being done at that time. We're not getting to that until after exam 2. We'll readdress it when we need to. But we still won't see it like this. All right, feel like that's enough background information. So let's go through Let's start talking about the terminology that is going to be with us from now until week 16, so December. And then if you're taking physics with me next semester, boy, buckle up, it's going to get worse. All right, voltage. This is our first real big term. We are going to see this a lot. Voltage and volts, though, we would like to clarify technically in circuits and in physics, they are two separate things. Voltage is defined as the work done per charge. So if you go through and look at a bunch of other things, basically it's related to how hard or how easy is it to move an electron from one location to another. So that is what voltage is. Our symbol for both voltage and volts is going to be the capital V. Because again, why not? So here we have this capital V here is our voltage. It is equal to W being work divided by Q, which is our charge. The voltage is the numerical value for the energy it takes to move the charge from one location to another. Volts is the unit. So 1 volt, so again, they both are going to use capital V. So if we're using numerical values in conjunction with variables, typically what you'll see is we'll drop those units to not confuse them. So here we have the volt, which is a joule per coulomb, or a watt per amp, or meter squared times kilogram per second cubed times amp. This is why we typically don't care about what's going into our units. We just say that it should be, or if I'm calculating a voltage, it should be a volt, because I don't want to have to try to figure out what those units are. If I'm being honest, this is not a complete list of all the different ways you can write out volts. So let's just say if I calculate a voltage, my answer is some sort of volts. So something you are probably going to hear me say in this class, and it has to do with the fact that physics doesn't call it voltage. Physics calls it the electric potential. Part of this has to come from another way we can describe voltage. So another way to go through and look at the volt kind of voltage is that 1 volt is the potential difference, or the voltage, between 2 points when it takes 1 joule of energy to move the charges to each other. That's a lot of jargon in there. Basically, it is a fixed amount of energy to move charges to each other. So that is why electric potential, I will probably say it because that's how I learned it. And that's what I get to teach it as next semester. So we'll see how this works out. But if you hear me say electric potential, again, it's the physics term. It has to do with how the volt is explicitly defined. We're not going to worry about this equation for voltage. We're not going to worry about all the units that go into the volts. But we do need to understand that we will be dealing with voltage all throughout this class. Voltage, and what we'll see it with current as well, both have dragged around some archaic stuff associated with them. So before we see the stuff that voltage has brought with it from the past, any questions on voltage or volts so far? So a voltage source, so that can be a battery, it can be from you just separating charges if you have fuzzy socks and kind of drag your feet around on the floor, whatever it is. There are many different places where you can create a voltage source. When we go through and have them connected into a circuit, we have this thing that sometimes we refer to it as an EMF. Where EMF here stands for electromotive force, and it uses script E as its variable. So what happens? We take our voltage source, we connect it to the circuit, and that voltage source is then going to be responsible for the charges moving around. If we go through and look at Newton's second law of motion, it says that a net force is responsible for an acceleration of an object with mass. Electrons have mass, not very much of it, but they have it. And so a net force is going to cause it to move around. Technically, voltage, even though it's sometimes called an EMF, is not actually a force. It is a potential difference. So what it's really doing is electrically, what a voltage does is it basically introduces a hill into your circuit. Where at the source, it's like you're at the top of the hill. And so, right, objects roll down hills, the charges move through the circuit, and then get back to that source. Good news is we are going to be dealing primarily with the ideal sources. So, especially when we deal with batteries, constant value throughout the entirety of it. We are going to exclusively deal with batteries, I want to say, for over half the class. We're not going to get into other non-battery sources for a while. When we get to those other ones, we'll talk about how those are ideal as well. We're going to see both DC and AC voltage sources. So for our battery, and we'll talk about what these symbols are in a little bit, we'll be seeing it represented like this. And very often next to it, you'll see a VS next to it, which stands for voltage source. The circle with the squiggly line in it is our AC voltage source. So this is going to be our alternating current. We don't need to worry about that right now. Basically, all it does is we flip it back the current direction back and forth. The good news for both of these sources, but in particular for DC, is I don't care how it works. It's not a chemistry class. We have done all the chemistry we will be seeing for this entire class in the past 40 minutes. That is it. We just needed to talk about the atom, and we are done with our chemistry. We're not going to care how batteries work. We're not going to care about the type of battery. We're going to draw this diagram and explicitly not care what it is beyond that. So this set of parallel lines to us is the battery. I don't care what type. I don't care what the reaction is. It's a battery. They are all going to be the same to us. Questions about voltage? Let's talk about the current. So what we have here on the right is we have an image of some sort of conductor that has a bunch of electrons that are just roaming about. This is our sea of electrons. So they're just electrons, they're just kind of there, and they're just kind of moving around randomly. So no voltage being applied. Basically, what's going to happen is your electrons, we go through just so you have, right, your structure, assuming it's silver or whatever, right? You have your structure and your electrons are just going to be kind of randomly bumbling about. I don't know why Excel's being bad today. So you're just going to have your electrons kind of just kind of randomly moving about. They don't ever get terribly far away from where they started. They can, but they're just kind of doing the random walk. So they're just kind of wandering around, bumping into stuff, not getting very far very fast. When you go through and you then apply a voltage to your wire, what this is going to do is it's going to start causing the electrons to move. So let's talk about the picture, then we'll talk about the bullet point. So with this particular picture here, we have applied a voltage such that on our left side it's negative, on the right side it's positive. And as we talked about very briefly earlier, negative charges are attracted to positive charges. Opposites attract. And so what's happening is all the negative charges are now moving towards that positive side. Now, in a circuit, if it's closed, this technically becomes infinite because basically as the electrons move, you're kind of moving where that positive looks. They're always just kind of chasing that positive charge. Now, something we'll talk about for current in a little bit, and this is the archaic thing we've dragged around with current, is when they were first going through and figuring out stuff with circuits, they thought the positive charges moved. We then figured out a little bit more and figured out it was the electrons instead. So with that, the equation for current is the same regardless of which one you're going through and talking about. But we do just want to understand that there is what is referred to as the electron current, which is the electrons causing the current. And then we have what is referred to as the conventional current, which is the current of the positive charges. So it's as if the charges, the positive charges, are moving to the left. Talk about that again today because it's we need to be very specific about which one we're talking about. We'll come back to that in a little bit, but just for right now, understand two charges, same equation. They're both defined current. Naturally, of course, the most logical answer we can use, letter we can use is I. So I for current, it's equal to charge, which is Q, divided by time. That's how much charge passes through an area per second is typically how it's measured. Current in this class is always going to be in some variant of the amp or the ampere if we wanted to be complete with its name. So with the ampere, again, if we think back to last week, amps are technically a base SI unit. The coulomb is technically the derived unit, but we have 1 coulomb per 1 second. So we're going to come back to current in a couple of slides here, but first we're going to introduce our resistors. But are there any questions about that? So about anything circuit related so far? All right, so resistance is going to be our opposition to the current. This can come from multiple different things. This image down here is a cutaway image of a resistor, which we'll get to in a couple of things here. This is going to be the primary mathematical thing that we're doing for resistance is the resistor. We're going to address it for currents in about half a second, and then we're going to probably ignore it and focus primarily on the resistors. So in a wire, as things go, as they move, you're going through, and those electrons, even though they're all roughly moving in the same direction, there's a chance that they're going to collide with an atom. And so when they collide with an atom, they're no longer necessarily moving in that nice straight line. So it's going to slow it down. You can have imperfections in your wire. So maybe you have a little notch cut out of it on accident, and now the electrons have to go around that. Just any sort of thing, like there's a bunch of different ways that you can have your electrons colliding with something inside. It doesn't have to just be an atom. It can be another electron. All resistance is measured in the ohm, which is going to be using the Greek capital omega, or the horseshoe. It's 1 volt per amp, kilogram meter squared per second cubed amp squared. Again, way too many different variations of it. If you're dealing with resistance, it is some variant of ohms. Don't worry about the subunits that build up into ohms. So if we look at our picture here for our resistor, there's a couple of different things that are labeled. Not that you might be able to read them from where you are. So the two wires coming out of it, those are referred to as the leads. So when you buy a resistor, it typically has wires going into it. That's not something you have to put in there because it has some sort of, depending on the type of resistor you have, depends on how it's being held in place. You have an insulating coating, so the outside of the resistor has some sort of insulator on it to prevent electricity from going in other directions. Inside, you have, again, typically some sort of carbon-based composition inside of it that is going to be somewhere between an insulator and a semiconductor, depending on the value that you have. On the outside, on this insulated coating, you will have this thing called a color band. With the color band, we'll talk about it a little bit more on the next slide. But basically what they are is you are trying to introduce resistance with resistors into your circuit. So you put this resistor in there, and you don't want to have to measure the value every single time, or you don't want to have to go through and try to find the schematic. So in theory, I personally disagree with this statement. You have these color bands that in theory you should be able to look at and say like, that should be this numerical value for the resistor. The resistor's resistance. I find that is very difficult. So we'll look at some resistors in the lab tomorrow. We'll get the kits out, and you'll see that some of those colors don't really show up great. Colorblind, it's even worse. We aren't going to deal with them very often in this class, but you can have a variable resistor that looks a little bit different. So primarily what we're going to deal with in this class is the fixed resistor with a set value. So let's go ahead and let's look at what that's going to be. But before I do, any questions about resistors? So these are the color bands for resistors. In no way, shape, or form am I going to ask you to memorize this. If you look at the packet on page 3, there is a kind of all-encompassing one picture version of it that's not from the textbook. This is from a resistor company. So with it, it's on this homework. It is on the quiz. It's going to be a multiple choice question on the quiz. I will tell you what the colors are for the quiz. Textbook doesn't do it for the homework, but if you need help figuring out what colors what, please just let me know. So with these, the idea is that you figure out how many bands are on your resistor. So you can have 3, 4, 5, or 6 bands. You figure out which one of these you belong to. So let's say we're looking at a 4 band. You would look at each band. The one's going to be further away. You would put that one over to the right. You would look at your first band. You're going to look for, in this case, it's green. So I'm going to look for green, and it's looking at the first band. So that would be a 5. I then look at the second band, which is red. So it's going to be a 2. So now I have 52. I look at my third band, which in this case is the multiplier band for the 4 band one. That's blue. So I move over here to the multiplier column times 1 million. So 52 million ohms. I then go over here, mega ohms, not million, mega ohms. Then I go over here to tolerance. I try to find that one. I think that one's technically supposed to be gold. I look at gold, I go to tolerance, plus or minus 5%. That is how you use these tables. Again, you check how many bands do I have? Once you figure out the bands, you can go through and look at some colors, coding stuff. We will try that. Yeah, you're doing it on the homework. So I'm trying to remember if we're doing it on Thursday or not. I don't remember if we're doing it on Thursday. We might be doing one. So this is what color bands are. Like I said, this week, never again. Yes. So depending on, so the idea of the tolerance is it's telling you it's between like plus or minus that percentage. So if I'm at 52 mega ohms plus or minus 5%, I can be within that band. All resistors, I think it's over 40 degrees Celsius for this dial breakdown. So there are some other like weird things that aren't on here that you're supposed to remember. So like that tolerance, as it gets hotter and hotter, tends to start spreading more for cheaper resistors. So when you're dealing with the ones that have the resistance band on there, or the tolerance band, that is going through and saying that up until it basically, they tell you it's not supposed to work, it should be within that percentage. Then if you look at the 6 band one, that does have a temperature thing on there that goes in addition to that. Because it's cheap. Yeah. That's I think all the resistors that are in the lab kits are 4 or 5. We won't be using those, but those are just like the cheap. It catches on fire, you don't care, you throw it away and get another one. So typically they're the cheaper ones, more expensive the more bands you have. Any other questions about resistors? I promise today's the last day I just talk at you for an hour and 15 minutes. We'll do examples next time. All right, electric circuit. Here's a picture. Please do not do this circuit. It's a bad idea. You don't need a car battery looking device for a light bulb. You can do a light bulb with a 9-volt battery. It works just the same, I promise. Don't do this. This is a circuit. It's not a very complicated circuit, but it's a circuit. I have a voltage source. It is completely connected. So I'm starting and ending at the same point, which is my voltage source here. So I've made a loop. And I have a circuit component in here, which in this case is a light bulb. Now, something I want to clarify before we get any further, a light bulb is a special resistor, especially if you look at some older light bulbs. So if you look at kind of some of the first iterations of the light bulb, the reason they lit up is because basically the resistor got so hot, it would change colors. It would, and then acts as a light source. With more modern lights like your LEDs, they don't do that exactly the same. So in that particular case, you're using semiconductors to go through and create light by exciting and letting the electrons fall back down. It's a little bit different, but you're still using, it still does some resistance properties with it. Bless you. So with this circuit here, I want to call attention to the direction of the arrows and think about what this textbook is called. So if we look at it here I have the positive end of my battery, and I'm drawing my current as if it's coming out of the positive end of the battery. This is the conventional current. So what is being drawn here is this is the moving positive charges. You can say that because it's coming from the positive side of the battery. This, again, with the positive charges, this is referred to as the conventional current. What we used to think happens, we know it's not the case now, but I promise you part of the reason we've kept this has to do with some magnetism stuff that we're going to get to when we look at the inductor. So I think that's week 12 or 13. So in a while, it'll pay off. But for now, this is the conventional current edition of the textbook. This is going to be the current that we deal with a majority of the time. If I wanted to look at the electron current, the only difference, right now it's the negative charges that's moving. Numerically, it's the same. The only thing that's going to be different is the direction. So if I wanted to look at the electron current, it would come out of the negative side and just kind of follow in the exact opposite direction. There will be times in this class where we're going to have to guess what direction the current is flowing. It's totally okay to guess incorrectly. It's totally okay to use the electron current instead of the conventional current. All that's going to do is it's going to affect the direction the current is flowing. So if I want to do the conventional current, I'm going to go around this one in particular, the clockwise direction. How I set up my math is going to look pretty much exactly the same as if I did the electron current. It's going to look almost identical. Just I need to go around counterclockwise instead and multiply everything by a -1. So the question is just going to become, do you want everything to be negative or do you want everything to be positive? We should put an asterisk on that. That's not going to be how it always works out. Right? We will have positives and negatives mixed, but how we approach those positives and negatives is just flipped from each other. The only thing you have to do is once you commit to either the electron or the conventional current, you are committed to the end of the problem. Like I said, this textbook is going to be doing the conventional current. It's primarily what I'm going to be going through and teaching you for going through and doing the math and setting everything up. Again, I promise you it pays off a lot more later when we go through and introduce different aspects of the current. But for right now, unfortunately, it's just kind of this weird thing that we're going to do for a little bit. Any questions on the two types of currents? Couple more things. Briefly, circuit diagrams we're going to be going through. As we introduce new components, we'll go through and we'll talk about them some more. But basically, it's just a way to go through. It's not to be lazy. It is a way to go through and take what the actual circuit would look like and draw it as a schematic. So if we look at both of these here, so this one, we have right the battery, a switch, and a light bulb, and it's switching between on and off. That's what the two differences between these circuits. For this one here, we're in the on position. So if we look at our switch, it is closed. This means that this is a complete circuit. Current is going to be able to flow. We're not going to be dealing with a lot of light bulb symbols, but the light bulb's on in this case. Here we have the switch and off. So now our switch is open in the diagram and the light bulb does not have color associated with it. We will build these up as we go through and talk about them. I am going to show you a picture. I would like you to not stress out about the picture. As we see these circuit components, we will talk about them. Okay? These are the symbols this textbook is going to use. We've got batteries, resistors, lamps, bunch of different types of grounds, bunch of different types of switches. You've got your voltmeter, ammeter, or ohm meter, fuses, things like that. These are typically the symbols you will see in this textbook. This is not an all-encompassing list. This is just some. So we'll see them when we get there, but I just wanted to let you guys know that everything that goes into a circuit has a symbol. What do you think it is for a wire? That one's not on here. Yep. That is the only one that I would like you to walk away with today is the wire. It is a line. Talk about the battery again next time. Talk about the resistor again next time. Wire, I'm just going to accidentally just do. I will forget that we haven't talked about it explicitly if I don't do it today. So wires, the closest one-to-one representation in a circuit to the diagram. All right, I have one more slide, and then we're going to be done for the day because I know it's just been a lot of information vomit. We are going to see sometimes in questions in this textbook where it's going to have our beautiful ohm meter, ammeter, and voltmeter inside of the circuit. And it's going to ask you, what's the ohm meter going to read? What does the ammeter read, or what does the voltmeter read? So we're just going to quickly address what they measure, and then we'll call it good. Based off of name and name alone, what do you guys think the voltmeter measures? What about the ammeter? That measures amps. Ohm meter measures resistance. And then there is the multimeter, which is going to be what you have in your lab kits. It does all this and more. So it can do a little bit more than that. So typically, especially if you're one of the people interested in circuit stuff more so, or electrical engineering, you are going to be almost exclusively in this day and age, you deal with a multimeter. So for those of you who are checking out kits from the library, you're not going to see it. I'm going to pull out for the people in person. I will pull out some old voltmeter, ammeters, and ohm meters just so you can see what it looks like. But they are not quite as useful, but they will show up in circuits for questions. Again, they'll ask you, what does this thing read? Look at what the first couple letters are. That's telling you typically what you're looking for to help you go through and solve. And we'll talk about how these need to be inserted into the circuits as we go through and build up kind of how resistor circuits work out. Any questions about the chapter 2 content, vocabulary, units, anything along those lines? Right? If there are no questions, I will see you guys next time, which again might be lab, it might be lecture.